Alright friends, welcome back to the function slides. Let us finish them up. So we talked about a lot of stuff last time, the stack, references, and bringing everything together into a bunch of different files. Lovely. Let me teach you some more tricks. So the next thing is const parameters, and this is useful when we have references especially, because maybe we like the idea of passing along references because they give us memory savings. We don't have to get anything copied when we pass it along. But the second you pass along a reference right now, right, like int ampersand I, let's say, I++ in an inc function, then you're allowed to modify that original variable, and maybe we don't want that. We just want the memory savings. The trick, if you want that but not the modification ability, you can use the const qualifier for your parameters, okay? And the reason this works is because you can convert any value into a constant version. You can always up-convert it into a const. And let me show you that. So for example, if I have int x equals 42, I can immediately go and say const int y equals 42. Equals x. I can put x into a constant just fine. I can always convert a non-constant variable and put it into a constant one. And so this works just the same for parameters, for function parameters. Okay? So you can pass regular variables, like normal ints, to functions that accept const ints. That's totally fine. And what that means, especially when references are involved, that those functions can't change that parameter. They're no longer allowed to change that parameter's value. Okay? So it's super nice when you have references because you get that memory savings, but you also don't get the ability to modify things. Okay? And so this is very, very helpful. It saves memory and it makes sure that you don't accidentally touch anything. So my recommendation to you is to always use a const reference for your parameters unless you have convinced yourself otherwise, unless what you're trying to do does not work. Okay? That will help you not make any mistakes when you're using normal references. Okay, so let me give you an in-depth example of that where we sum a vector, a function that takes a vector and sums all the values and gives back the sum. Okay? So let me make a vector here. I guess I'm going to need to include that library. Vector int v equals 8675309. So that's my vector, and let me make a sum vector function. We can give v to it, and it gives back the sum, and maybe we can print that. That seems good to me. And so normally, before we learned about references, we'd be like int sum vector takes a vector of ints, call it v, and then it does its work with it. But we want memory saving, so we'll use a reference to a vector, so that'll work better. Sum equals 0, and then for every element in v, add it into the sum, and return the sum. But the issue right now is that we are allowed to modify v. We can say v at 0 equals 42. We don't want to be able to do this, because this is going to modify the original vector v. You see that? We don't like that. We don't want that to happen at all. We just want the memory savings of using references without the ability to modify the thing that we passed. Okay? This is allowed right now. To make it not allowed, we can use const. We can say it's a constant reference to a vector. Const vector int v, and now this is no longer allowed. It is a constant. We have up-converted v from a normal vector to a constant vector, and inside of this function, where it's const, we're not allowed to touch v. We're not allowed to set anything inside of it. So, isn't that nice? Assignment of read-only location. And so it won't even compile when you try to do that. So that's what const is good for. It makes it so that you cannot touch your reference. So you saved memory, but you didn't lose anything. And apparently the sum is 38. So with that, let's keep on chugging. That is const references. Very, very useful. Use them as often as possible because of the memory savings and the fact that you cannot hurt yourself by using the reference anymore. You cannot change that value. Okay, let's move on to something that is normally a topic of CSCI 41, but I want to get you thinking about it right now because you're ready. I'm not going to test you on any of this little subsection of these slides though, okay? This is just something I want you to keep in the back of your mind. It's called algorithm complexity. How complex is a function, is a program? And complexity has to do with speed as well, right? If a program is more complex, it's going to take longer to run. So you might be wondering, okay, how can I tell how fast my program takes to run? Well, you could use the ctime library. There are some functions inside of it to track how long it takes to run a certain piece of code. You can start a little virtual timer, stop it. Definitely take a look at that library. It's cool. But that's going to tell you, like, okay, it took 5 seconds to run this program. It took 10 seconds to run this other program. But the issue is, you can run a program on your super fast computer, and you can also run a program these days on your toaster, right? Each processor is different. Maybe your toaster is not as fast, right? Which means the entire program is going to be slower, but really it was the same program. How does that deal with complexity anymore? Just timing something. So there's a better way. There's a better way to talk about the complexity of a program rather than timing the number of seconds it takes, because the same program running on different processors might take a different amount of time, and that shouldn't be how we measure it. Okay? So let's talk about this, because regardless of processor speeds, right, some programs, like infinite loop programs, of course, are faster than others. Some are not going to ever finish as well. So the way that you can talk about, regardless of a processor, how fast a program's running is to count the number of what I will call basic operations, things that will take a single step of execution as far as a processor is concerned. And don't worry if this is all going over your head right now. This is all a topic of CSCI 41, and I'm not going to test you on it, but I want you to think about it, okay? So how long does it take for each step to execute? Count all of those little steps, and that becomes your program. And we'll have a mathematical expression of how fast it takes to run it, okay? So a basic operation, let's say all of these are basic. Doing addition, arithmetic in C++, that's a basic operation. Comparing two things in C++, that's a basic operation. An assignment statement, like set x to 42. That assignment process, let's say that takes one step of execution. Same with printing to cout. Let's say that takes one step of execution. And I'm definitely sweeping a lot under the rug right now, but this is still something that is morally correct, even if it's not perfectly correct. All of these things really do kind of take one step of execution. So here's an example piece of code. So int x equals y mod 2 plus z, and then let's be like cout x, something like that. So let's count all the basic operations here. We have a modulus, y mod 2, that's one basic operation. Then we add that result to z, that's another basic operation. Then we assign all of that to x, which is a third basic operation, and then we print out x. So that seems like 4 basic operations. And that is always going to essentially be 4 basic operations regardless of the processor that you're running this code on and how fast that processor itself is. Like maybe your processor is 2.4 gigahertz or something. That means it can run 2.4 billion basic operations every second. That's what really that number means. Okay? Some things are not basic operations though. Here are some of them, like summing a vector, because vectors have different sizes. There's a different amount of work you have to do for a different sized vector, so that's not a basic operation, doing all that at once. You have to go a bit more fine-grained there. Also, calling a function is not a basic operation because you have to count all the basic operation in all the basic operations in that function's body, right? Because you're going there, you're running all of its code, and there might be a lot of it. Same with reading a bunch of ints until the user types -1. That's a loop, right? You have to count how many times this is really happening. how many times the body of that readInts loop is running. Okay? But for most intents and purposes, you can assume that every single line of code that doesn't do anything super fancy like call a function, you can assume that it's just made up of a bunch of basic operations. And really, at the end of the day, you can consider this to be just one big basic operation. It all works out in the end. So let me give you some experience with that kind of counting. See if you can figure out how many basic operations are in this loop. So give that a try using these definitions of basic operations. Okay? So assuming you've taken some time to try and count them, let me talk to you about how this is all working. So a for loop, remember how it executes. It takes, it runs this code just once, and that is a single basic operation, right? This is an assignment. And then it repeatedly makes a comparison. That's another basic operation. Then it runs the body. It's printing two things maybe, so two basic operations to run that body, right? So that's going to take two basic operations. And then after every iteration of the loop, we run I++, okay? Which is secretly how many basic operations? It's secretly I equals I plus 1, so 1 for the plus, 1 for the assignment. Oh man. So counting the total number of basic operations now, it is going to be 1 for this line, 1 for this first line because it only happens once, and then, well, how many times is this loop going to iterate and run the condition check, or how many times is it going to run its body and do I++? A lot of stuff going on there, right? It's going to run it exactly n times, right? Because I is going to go between 1 and n, so it's going to run its body n times. That is like exactly n times running this, which is 2n, right? Because two basic operations done n times, and then another n for each I++, right? And then another n for these comparisons. Gonna have to do it n times total, and then one more, because I is going to get so big. One last time, I will get to become n plus 1, and we'll have to notice that and stop the loop. So if I'm counting correctly, there's one extra comparison happening. Okay? So this is essentially the number of basic operations that are taking place in this code. It's involving the variable n. Do you see that? So 5n plus 2 steps are being taken. That is a number that has nothing to do with how fast a processor is. It's just, this is how many steps it takes to run this code. Do you see how that's a nice thing to have, a number like that? And really, when we get to 41, we're not going to really care about all of these constants. We're just going to notice that, okay, this grows as n grows, it grows linearly. It's some constant times n, and that's really what we care about, that kind of linear growth versus some other kind of growth. Okay, so yeah, here's the strategy. If you care, you count the number of basic operations in your code, and then you write a formula for that program, like how many basic operations it will take, in terms of a variable usually, like how big the input is, how many things you're getting from the user. Usually we call that n. That is the standard variable that we use here, but it helps us compare how long it's going to take to run different kinds of programs, because here's the number of basic operations to do a bunch of different things. And again, don't worry if this is going over your head too much right now. This is a CSCI 41 topic, but I think a lot of us are ready to start thinking about this stuff, okay? So, and I want you to at least try. So here are the number of basic operations to add two integers, right? That's going to be a plus operation, right? That's a single basic operation, 1, and it's going to take one basic operation no matter what. We call that constant time. It's a constant number of steps no matter how big those ints were. They're just single numbers. To sum together n numbers, you have to do a loop that runs n times, putting them all into a sum variable, right? That's going to take n times some constant, where you're doing some work with assignment and plus and all that. We call that linear time. It's a linear number of basic operations, growing as n grows linearly. If we're trying to create a box, like an n by n box of numbers, or stars, let's draw a box of stars, you have to have a nested loop for that, right? Which is going to involve going through n squared iterations of the inner loop's body, which is going to print stuff some number of times. So it's going to be a constant times n squared out in front of your mathematical expression for the basic operations. Do you see how this is definitely going to take more time than this one? It's more complex. We call that polynomial time. Okay? So try and think about this as you're writing your programs. Like, okay, I'm adding a bunch of loops. What's that doing to the complexity? And this will prepare you greatly for when we take CSCI 41. This is going to be one of the main topics of that class. So now you know about it. Okay, so that's algorithm complexity in a nutshell. Feel free to ask me more about it during office hours. I'd be happy to speak more to it. Okay, so the very last section of the day that I would like to get into is just going through algorithms some more, just how to come up with the solution to a certain problem, okay? And I want you to think about them in a new way. I'll teach you a new way to think about programs and writing them. So think about the problem you're trying to solve in terms of a bunch of states that you can go between, like my program is in this state, and then it goes to this state, it does something else, and then it goes to this state, it does a third thing, and maybe it goes back to the first state. And it moves around in between states using commands. Okay, this is a new way of thinking about a program, and if you can get it into this form, not all programs can be translated into this kind of state machine way that I'll talk about, but the ones that can, it becomes very easy to solve them. Okay, so see if you can find that in problems that you're working on. So here is the idea. There's a bunch of different ways to write a program. We call those ways architectures, program architectures, or program patterns, software design patterns. Those are the terms that you can look up on Wikipedia or something. There's a ton of those, and they're just methods for designing programs that look nice, that people enjoy reading all the code of. And nobody thinks that there is one true way of writing a program. Everybody has their own preferences, but here's a cool one. Here's a cool one that you haven't heard of before, most likely. This is a nice way to like follow a few steps and build a very easy to write program. Like it's a nice looking one, it's cool looking, and it is most likely very correct as well. It's easy to reason about. So it's called a state machine. Okay? So it's when you have a bunch of states that you can go between and a bunch of commands that move you between states. It's going to help you abstract away the process that you're trying to fulfill. Okay? So here are two different example state machines, and let me teach you the terms before I explain them. So a state machine has a bunch of states. These are the circles here, or the little rounded rectangles here. Those are the states that your program can move between, or that the process you're modeling contains. And then you can move between states following arrows. Those are called transitions. Okay? And once you know about all the states and all the ways to move around with them, a state machine, when you draw it, it tells you exactly what your program can do. Isn't that nice? That's super nice. So here is a simple state machine. Let me teach you all these things. So let's pretend we're modeling a person. And so maybe we're born at home, and so there's a concept of a start state. And so maybe our starting state is the home state, all right? And then if we want to take a transition, maybe we wake up and it's time for work, we need to get to the work state. There's only one way to do that. We'll follow the take train transition, okay? And then now we're sitting in the work state, and we can do work stuff. Maybe as long as we have work, we stay there, so we can remain. We can follow a transition, like the do work transition, who knows, to stay in that state. But once work is over, we want to go home, right? To transition back to this state, we'll take the train again. Okay, does that make sense? And so this the state machine is telling us exactly what we can do. For example, we can't go straight from work to bed. There's no path there. There's no transition straight there. We have to go home first. That's where our bed is, right? And then you can go to sleep, wake up, go to work, stay at work, all this stuff. These are the possible transitions you could follow. Maybe it's the weekend, and so you'll sleep, wake, stay at home, sleep, wake again, and then it's a weekday and you can go to work. Maybe you forget something at home while you're at work, and so you have to go back. So these are the kinds of transitions you can follow, and it's helpful to think about all the possibilities you could take. And you're kind of constrained. You can only do the things that are spelled out in the state machine. Do you see how that makes for an easy way to reason about a program, if you can model a program as a state machine? And here's a more complicated machine for like how like an Uber app or a Lyft app works, like when you're asking for a ride from somebody. You like maybe the app puts you, when you request a ride, into the trip requested state, and then in order to actually get somebody like your Lyft driver to show up, it's going to run your credit card, and so it's going to request a payment, and so then you're in the payment state while it's working on that. And if it succeeds, then it's going to give you a driver and they're going to come to you. But if it fails, then you have to go back to this state, and maybe it's going to ask you to insert a new credit card number. And so you're not allowed to get a driver as long as the payment hasn't succeeded. Do you see that? That's easy to reason about. And then maybe the trip is over, then the driver becomes unassigned. Another way to have an unassigned driver is like the customer canceled. You can move to that state. Things like that. That's how you can model, like maybe the Lyft or Uber people are modeling the way that their app can work with a state machine. And so you can reason about how these programs are going to execute quite easily when we have these. Okay, so let me give you some more examples of state machines, and then I'll give you one good example that I learned in my CSCI 40 class that I will teach to you now. Okay, so here is another example. Let's pretend like we're writing a program always. To create a state machine for that program, we group the program itself into a bunch of states and a bunch of actions that can move between states. Okay? So like let's pretend, let's try and make a state machine for you as a student. So maybe as a student, I think of you as a two-state machine. You have a learn state and a practice state. Okay? And you alternate between them when things get posted. So the second you come to class, like there's no assignments yet, so you start out in the learn state, that's your start state, and then like when things get assigned, I assign a lab, then you are going into the practice state. Yeah. And so you just do your work while you're in that state. As long as you're not done, you can stay in the same state while your lab's not finished, things like that. Or when a lecture starts up again, then you have to go back to the learn state, right? And you stay there as long as the lecture's not finished. And so this is a kind of state machine that models your life as a student in this class. Isn't that cool? And yeah, we can have the concept of a starting state or an initial state. That's the learn state. We can model it that way. And then the very end of this class will be the final, right? And so there's nothing more for me to teach you. You'll be taking the final and you'll be practicing while you're doing it. So your last state, when you end this class, your final state will be the practice state. And you can represent that in the diagrams by making a double circle. Okay? So that is a state machine. Hopefully it's starting to make a bit more sense. You can model anything with a state machine, for real. And so what I'd like you to think about is how can you make a state machine for a traffic light? Because really, we want those to be very safe, and we want to make sure that like you can't go straight from you can't go from yellow back to green, right? That would make no sense. So there are only certain states that you can follow in a traffic light to make sure that nobody's going to get hurt. So see if you can finish the state machine for this traffic light. There are a bunch of different correct answers, and I'll talk about one of them, but I want you to try this, okay? So here's kind of what I would come up with. Maybe, I don't know, what's the start state? Let's think about that. Is there a concept of a start state? Like maybe when you turn on the traffic light, when electricity gets first turned on to the traffic light, it wants everybody to be super safe, so it starts out making it red for everyone, and then it figures out who should go first, right? And that could be the starting state of a traffic light. And then, like, people are sitting at the light, red lights can only then become green, right? Assuming we're in the US. So, like, maybe this is a transition that gets taken place when there's been a car waiting at the light. Remember to label your transitions, like what causes this to happen. Maybe a car was waiting for a minute, and that's how long it takes for our traffic light to change. Okay? So then green, we let the cars go, and maybe then we're going to stop them and let somebody else go, and so green goes to yellow after maybe 20 seconds or something. And then it stays yellow for a little while, a few seconds, like 3 seconds later. then it goes to red and this all repeats. Does that make sense? So that could be a state machine for a traffic light, and you can think about it like more things could go wrong, right? You could model this really well with a state machine. Like maybe if there's the power goes out, if there's an electrical failure, and we go on the backup battery for the traffic light, we want it to just start flashing red and stay red, okay? To keep everybody safe like that. So this could be a more complete state machine for a traffic light. You see how there are options? Nothing is perfectly correct, but it really helps you think about the program and the actions that the program could take. We cannot go straight from red to yellow. Things like that. We can't go straight from yellow to green. Those are impossible transitions, and we can spell that out with a state machine. Okay? So finally, let me check my time and everything. Plenty of time. So I would like to teach you a state machine example that I learned as a CSCI 40 student at Fresno State. So I'm passing this on to you now. It's a cool little example of using a state machine to count the words in a string. Okay? And I promise this is a very interesting problem. It's not as easy to solve as you might think. It has a very elegant solution with a state machine. So let's say we get a line from the user, and we store that in like the line variable or something. And so it's going to be a very long string, and you might be thinking like, oh, it's very easy to count the words in a sentence and a line. I can just count like the number of spaces or something. So here's like a single space. I'll use that to mean a space. Hello, comma, space, world. And I'll like add 1 to that count. Let me ruin your day by adding a bunch of extra spaces. Here's like blah, space 42. So there's really 1, 2, 3, 4 words in this sentence, and I have ruined the day with a bunch of extra weird spaces. I'm going to teach you a state machine that doesn't care, that will correctly find the correct number of spaces, or the correct number of words in the sentence, okay? And so here's the trick. Here's what you do. You read the characters of this line one by one, and then you keep track of whether or not you've seen white space, any kind of space character, a new line, a tab, a space, it doesn't matter. And that will help us transition and eventually keep the correct count, okay? So here is the key idea that's going to inform our state machine as we build it. The idea is that white space, when you see it, it is a word separator still, right? Even if there's a bunch of them, white space really has to appear before a new word. So white space separates words, maybe multiple white spaces though. And each non-space character though, it's either part of an existing word like the E, the L, L, O, or the start of a new one, like the W or the H. So let me show you the state machine now. There are 2 states, and this will correctly count the number of words in a sentence. So here are the states. You're either in the outside a word state, or you're inside a word. You're in the inside a word state. And the transitions between these are going to correctly count the number of words total. So when we start reading, remember that we're going to visit every character in order in this line. That's how we're going to give input to our state machine. The second we begin, we haven't seen anything. So we haven't seen any words yet. So let's start in the outside a word state. That's fine. Then when we see a non-space character, right? We see an H, we see a W, and we've been outside a word, we just saw a new word, right? We are now inside of a word. So we saw a non-space character. Okay? And then we remain inside of a word as long as we keep seeing those non-space characters. Like I see the E, the L, the O, the comma. I'm still inside that same word. So again, with the non-space characters. That'll keep us inside a word. And then, okay, when, after having been inside a word, like we've seen all these characters, when do you begin to be outside a word again? Well, D exclamation point still inside of this world word. The second I see white space, I'm now outside of a word again. You see that? Whee. So the second I see a space, any kind of space, I'm outside a word, and I remain outside a word no matter how many spaces I see. If I'm already outside a word and I see more spaces, I'm just still outside of a word. See how that elegantly solves the problem of multiple spaces? And now the question is, how do we use this state machine to keep track of things? Because we're eventually going to have like a count variable for the number of words started at 0. Which of these transitions notices a new word? Do you see it? It's this one. When we are outside of a word and we see the first non-space character to start going inside of a word, we just saw a new word. We went from outside to inside. We just saw the first character of a brand new word. That's when I add 1 to count. You see that? The second I follow this transition, I've seen a new word, and I can add 1 to my count. Let me show you this working. So we start outside of a word, and then we see a non-space character. Oh man, counts 1. So now I'm inside a word, and I see the E-L-L-N-O, and I remain inside of that word, E-L-L-O, comma, because I just saw a non-space character. See that? The second I see a space, though, I'm now in the outside of word state again, ready to look for a new one. And if I kept seeing spaces, I'd stay there. But no, I see a W now. And so that follows this transition from outside to inside. I saw the first character of a new word, now counted as 2. Hey. So, and I see the O-R-L-D exclamation point, stay inside of a word, and then I see some spaces. The first space sends me here, the remaining spaces keep me there, and then I see a B. Bam, I'm inside of a word again, counts 3. I saw the third word. L-A-H stays there, space sends me to outside a word, I see a 4, and that is going to bring me into a new word from outside to inside. So that's the 5th word. Or sorry, the 4th word. And then I see a 2, and that's the end of my input, and so I just stay in the inside a word state. That's where I end, but I didn't see any more. So the final count is 4, and that is the correct number of words. Isn't that cool? Isn't that super cool? So, yeah, that is counting words in a string with a state machine. Let's go and implement it. Let's see how we're doing. Yeah, plenty of time to go and do this. So, count words. We're going to make a state machine. So, we have to put this in code somehow. Think about how I'm doing that while I get a line. So, string, also need CC type. So string line, and then it'll be like cout, enter a line of text. That'll be like get line, cin into the line string, and so now I have my line. And now I want to run my state machine, which will involve a count starting at 0. What do I do? What in the world will I do? So eventually, I want to make this a library to give us examples with all the stuff that we've talked about. So let me make a function first to count the number of words. String s, and let's practice references in const. So let's have a const string s. Let's count the words in that string. Give back an int, right? And so that's where I'll put my count and all that. I'll eventually return the count. So count words of that line. And we'll eventually separate this into a bunch of files. Okay, so let's implement this. How in the world am I going to implement this state machine? What does it mean to implement the state machine? Well, it just means you have to keep track of which state you're in, right? And then every time you read new input, every time you read a new character, you have to transition and change what state you're in. So to keep track of what state you're in, you can just use a variable. Be whatever kind of variable you want. I'll use a string. My current state starts in the, I don't know, outside. I'll just use a string to represent that I'm currently in the outside state, outside a word state. See how that is going to allow us to translate the state machine to what we want? And then I want to read all the characters of the string. So for int I equals 0, I is less than s dot length, or size, I plus plus, and so, I don't know, char, next char equals s at I, and so I'm going to use this next character to run the state machine. Depending on where I am, I'm going to change states. Okay, so we're going to do different things depending on what state we're in. So if my state is outside a word, then I'm going to do some stuff. Otherwise, that means my state was inside. And I'm going to do the inside stuff based on my next character. Yeah. So if the state was outside a word and I saw a space, I stay there. Right? And you can definitely simplify what I'm about to write. If is space next char, because it doesn't have to be just a space, it could be any kind of white space character, and is space from CC type will keep track of that. So if the next character is a space, then I remain in my current state. So state equals still outside. So I technically don't have to say this because it's already outside, but I'll just do it for fun. Otherwise, it's a non-space. What does that mean? It means I was here, I saw a non-space character, so I need to transition to this state and also add one to count. So state is now inside. I'm now inside of a word, and I just saw a new word, count plus plus. Isn't that nice? So that's what you do when you're in the outside state. That's how you transition. Otherwise, if you're in the inside state, here's how you transition. Let's keep all these. So if you're inside of a word and you saw a space, then you're going to outside a word again. So that's already correct. Cool. So state is now outside. Otherwise, if you saw a non-space character, you remain in the inside state. So state is inside. You don't have to say anything. This is already there, but you just follow this transition and stay there. And we're not adding to the count anymore because that's not the same transition. Okay, so this is the state machine. That's how it runs given a new input. Here's the new input. Does that make sense? That's all. And there's the for loop that runs that entire state machine and keeps track of the count and does all the cool stuff. So by the time we're done, down here, now we've visited every character of the string. Count is correct now. Okay, we'll return that count that we've built up. We've added one to each time we saw a new word. Okay, so that should do it. That's our count words implementation. And so I'm going to enter a line, and it's going to tell me the number of words in that line. And there's the code while we're looking at it. So what was my string? Hello, comma, space, world, space, 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 blah, 42. I can have as many spaces as I want. I can have even trailing spaces at the end. Not a big deal. Hit enter, and what do you know? We ran our state machine. There are, in fact, just 4 words there, and it works for any string. Isn't that cool? So, yeah, that is counting words in a string. That's a cool little state machine. We got practice with that, and now let's get practice with multiple files. Let's make this into a library, okay, with a bunch of separate files. So let's make a folder for this. Count words. That can be a folder for all the things that we're going to make. Let's remove the compiled file and move the C++ file into this folder. And so this could be part of the count words library. There we go. And so I want to separate this into implementation of the count words, declaration of the count words header. So this is my library. Remember to use our header file guards. My library will only have this one function called count words. And it needs to know about strings. And for reasons that I will get into later, I think, I can't just say using namespace standard inside of a header file. Because this is going to get copied and pasted, it's going to force somebody that may not want to use namespace standard to use it. So we'll just be extra pedantic here and say standard string. So that's the header file. And the implementation goes in the CPP file. That is all well and good. Let's make I guess I've been calling it main.cpp that actually uses the library. So let's take the main function there. There. And I also want all this stuff. So let's copy it, because I'm going to need it in that implementation of the library. So here are my 3 files now. This one no longer needs main, and I got rid of it, good. Customarily, we also include our header, countwords.h. It's a good habit to get into. And then here's us implementing the header, all the things in the library. Just the countwords function goes here in the corresponding CPP file. There's the implementation of my library. And then here's me using the library. Remember to import yourself, so include the header file so that it knows about it. Countwords.h. So now it knows about the function. Cool. And that's it. So now everything is still the same. So go into countwords file or folder. To compile now, we say G++, and then we give every C++ implementation file. Because remember that the .h files are all getting copied and pasted anyway. So give those files, and then we can call it whatever we want. I guess we can call it countwords. That's fine. Whee! And so it still works. 2 words. And that's my library. So definitely study that if you're still a bit fuzzy on how to break down things into files. The last thing that I want to do, let's get more practice with writing unit tests. So let's make a test for our countwords function. And instead of make even more files, let's just keep the ones that we have. I'm going to need my assert true, my handy dandy assert true function here. I guess I can steal that from this one. Yeah. So I'll take that, put it up here, and let's make a test for this. So I don't know, we can call it test countwords or something. Let's put it before all this stuff. So let's assert true. We can write as many tests as we want. Assert true that counting the words of a bunch of things like, I don't know, hello world, new line tab, space space, hi mom, 42. How many characters, or how many words is this? 1, 2, 3, 4, 5. So that should have given back 5. 5 words. That can be the name of our test. And then we can do as many tests as we want. We could be like, blah, spaces around it, try all the corner cases. So that's only 1 word. That could be another test. Count words of nothing, or maybe a bunch of spaces, or a single space. There are no words in that, right? So these are a bunch of tests for our count words function. Isn't that cool? If they pass, we can gain more confidence that it's actually working. And yay, it looks like they do. And then the rest of the program was still running down here. I'll just stop it with Control-C. But that is counting words in a nutshell. So the cool algorithm, the cool algorithm was over here, using that state machine. Hopefully that makes a lot of sense now. And that is where I want to leave you for the lecture. So, doing just fine on time. This is week 8, and that means it's the middle of the semester. So what I'd like you to do, if you have time, if you have something to say, I would really appreciate it if you filled out this mid-semester anonymous feedback for me. It's a form. It'll take you to Google Forms, and it's just for me. I can't see who writes what. Completely anonymous. It's not for a grade. It's just to give feedback about the class while there's still time to change things. So I would appreciate your feedback. So thank you in advance for filling that out. And I think that's all that I wanted to say. There's a lab this week, so I'll go and make that video, and I will see you there.